Hi everyone, I'm Jeff Alexander. I'm Jed's PhD student who's working on the xdift system for this project. So I'm going to give a quick demo here of what we have working so far. The demo itself is only going to take about 2 minutes or so for the code to run through the example trace I have. So before I actually run the demo, let me talk to you a little bit about the system as it stands now and how it's going to operate, how it's going to function. So our system is a full system stack dynamic information flow tracking system. It's built on top of a plugin built on top of QEMU called Panda. Panda is designed to try and make it easy to do kind of reverse engineering stuff for a wide variety of platforms in an architecture independent fashion. One of these is dynamic information flow tracking, which is what we're going to be using the majority of, but it also allows you to do virtual machine introspection, looking through running operating systems, process lists, and memory spaces, and things like that as well. So rather than build an entire system from the ground up, we figured it would be a lot faster and a lot more feasible and efficient to build our system on top of Panda's existing dynamic information flow tracking system rather than trying to rebuild everything ourselves from the ground up. So currently at the moment it's kind of in a middle ground where half of the code or half of the actual propagation logic for the information tracking is our code and the other half is the existing code. I'm working on trying to change that completely over to ours, but it's not quite there yet. So the way that this system handles dynamic information flow tracking is it starts up a modified QEMU binary, which is the actual Panda system itself, and then takes each basic block of the guest operating system's code and translates it into the LLVM intermediate representation language. This is very widely used, very well documented intermediate language. So hopefully will be pretty easy to use, and it's pretty powerful language. So we should be able to do some pretty cool, pretty complicated things if need be with it. So we're going to do all the information flow tracking on the LLVM intermediate language to try and keep the architecture independent nature of the Panda system intact. So once a guest basic block has been translated into the LLVM intermediate language, the information flow tracking system will then go over each instruction in that basic block and generate an equivalent taint operation for it, which it adds to a buffer of running taint operations for that basic block. Now these taint operations mirror the existing operations and carry out the taint propagation on the, if you want to think of it as kind of a virtual information flow tracking or taint tracking system for us. So once we've gone through a basic block and built up a buffer of taint operations, the LLVM intermediate language for that basic block is just-in-time compiled to the native host machine code and then run with some additional logging features that store any dynamic values that may be needed, such as memory addresses, the results of branch conditions, things like that, which we can't get without actually running each basic block. Once the system has finished executing the just-in-time compiled basic block, it then goes over the taint operations that we put in a buffer before executing the block, and actually does taint propagation, filling in any dynamic values that it might need from those that it logged when the basic block itself was executed. This all happens single-threaded, so there's no worry that we miss something because of some concurrency problems or anything like that. And once it's done doing the propagation logic, it then stores any results into a shadow memory, which shadows physical memory, any I/O ports that the virtual machine using, as well as all the intermediate LLVM registers, program counters, things like that. At the moment, the example system I'm going to demo shortly is currently just using basic binary tags. Either a byte is tagged or not, and we're using byte level granularity for that. In the future, ideally, we want to use more complex type systems where the type can change depending on the operations. But for now, as just kind of a first step to make sure we have something working the way we'd like, we're just doing basic binary tags for the moment. So for this particular example, the code is running on a trace of a Linux machine that I just booted to a command prompt, and then ran a handful of wget commands on network pages. The main one being the Google homepage. And then I instructed the system to tag and track all information coming from the network card into the system and keep track of it as it propagates through. And then at the end, print out all of the physical memory addresses that were actually tagged or tainted, however you want to think about it, at the end of the trace. So it's going to take about, I think it's about 1.5 minutes, maybe almost 2 minutes. So I'll start it running right now and then kind of go over and explain what's going on. So initially, the system has no taint coming in because it hasn't received anything from the network. And so it doesn't actually taint anything until it receives network traffic, which it turns on. As you see here, it's logging a handful of values for some helper functions that QEMU uses that the plugin is incapable of knowing exactly what code is running ahead of time. And most of these helper functions are not actual guest operating system code. It's host QEMU code designed to simulate underlying guest things like XMM registers for the x86 processor. So the system is tracking taint in and out of those helpers, but because it can't know which helpers are being called statically, it can't build up taint ops for some of them. So it does track taint, but it can't necessarily track them through the helper functions in QEMU because it's not the guest, it's the host. So as you see, it's going over the list of instructions, logging how long it's taken, how much RAM it's taking. Currently those RAM numbers are higher than they will be for our system, hopefully, because, as I mentioned, we're using kind of a mix of the existing dift system in Panda and our system. So we're kind of duplicating some of the tag stuff for portions of code that I haven't had a chance to get rid of and convert over to our system yet. For the final version, what we would like to do is use the existing dift system in Panda to handle all the emulation, but all the actual propagation logic will be our own. So that way we're not rebuilding from scratch or dealing with any of the multitude of optimizations QEMU tries to do to be efficient, which the Panda dift system handles, and any we built would also have to handle. And so rather than reinventing the wheel, and rebuilding and rehandling all those optimizations, we're just going to let the existing dift system do that for us, and hopefully still get really good performance out of it at the end. I redirected the output log of that run to a text file. So we'll look at that really quickly. And you can see here It lists all the areas of memory which were actually tagged using our tagging system that I've added on, not the existing system that Panda was using. And I've collapsed contiguous blocks of memory rather than being individual bytes into just large blocks of memory, and hex dumped a handful of them here so you can see what we're actually getting at. Now, a lot of these dots here are non-human readable ASCII values, so it's probably memory addresses, temporary values, things like that that are stored in memory that were tagged by the system. However, if we scroll down a little in this log file, you can see, as I mentioned, this was a wget of Google's homepage. And so we can see down here the initial response from Google to our initial GET request of their home site, or at least a part of it. It was, it's a full web page, so it's split across multiple packets. But this is the data section of one of those packets. You can see here, it's an HTTP response from when I made the trace a few weeks back, as well as a lot of the header information and meta content tags for Google's website. If we go a little further down, past some more memory addresses and things like that that were tagged, we can see kind of a continuation of that header, the beginning of some JavaScript here. And then further down, there is some more JavaScript, the rest of that website, the rest of that page in here. And then further down, there's even more. You will notice a few of these small little 4-byte, 8-byte kind of areas. This is also tracking information as it moves through the kernel and not just user mode processes. And this was with full system taint, full pointer taint. So the system is over-tainting pretty heavily. And I haven't had a chance to check yet, but I think a lot of these kinds of tags here are tagged information over-tagging and flowing into the operating system and operating system data structures, which hopefully once we get a full system up and running, our goal is to eventually be able to prevent that by being able to tell when we're dealing with operating system structs and when we're dealing with non-operating system structs, or only propagating for certain types of data. Hopefully we can make that as simple or as complex as we need. So that's what we have so far. Hopefully I was not too confusing explaining it, although I should be able to answer any questions you have. I think everyone has my email, or if not, I'm probably sure I'll be in on more conference calls in the future. So with that, thanks everybody for watching, listening, and let me know if you have any questions about it all. Thanks.